All right, let's finish up these proof slides. Let's do it. So what we were talking about was contrapositive. Like this is equivalent to this, and they're both implications, so like you can prove either one. You can like, in a direct proof, assume this, prove that, or assume this, prove that, and one way might be easier. So now you have options. All right, so that's a proof by contrapositive, and here I want you to try this. So let's prove the following statement by contrapositive. For any integers x, y, and z, if x divides y and x does not divide z, then x must not divide y plus z. See how this is like ugly with some negations of like divides in there? We know nothing about what it means to not divide. We only know what it means to divide something. So like, let's use contrapositive to like negate some of these stuff after flipping them. That's gonna make it easier, right? But this one's actually a little bit tricky, so let's visit the next slide before we prove it. I'm actually going to help you. We're going to come up with a proof statement first, and then I'll have you try the rest. So let's translate this to math first of all. So this is for any integers x, y, and z. So for all x, for all y, for all z, three variables quantified over. If this is true, then this is true. Right? So that's just the original statement. So we got if x divides y, and x does not divide z, then I don't know why I don't like that. I want a bigger slash, maybe. I don't know how big the slash should be. X does not divide z. Now that looks too big to me. I'm very picky about this. There, x does not divide z, then x must not divide y plus z. Okay, that's the idea. So that's your if-then. Way too many, what's it called? I started it, but I didn't finish it there. Way too many parentheses. And so we would like to create the contrapositive of this. And there's two things in the hypothesis, sadly, and one of them is fine. We don't really want to negate this, because it would, like, if we did the contrapositive in the normal way, it would be like, negate this implies negate this. We can do different things. We can make a different kind of contrapositive. So let's talk about the next slide first. All right. So you can make a contrapositive when you have multiple hypotheses, and you have options when you have multiple hypotheses, because, all right, you can do some cool stuff. So yeah, fine. We know this. We know that this is equivalent to its contrapositive like this. But what about this? Right? What about this? P and Q implies R. Well, that turns into not R implies not P and Q, right? Negation of the whole thing, which use a De Morgan's law, shove that negation inside, you get not R implies not P or not Q, right? Does that make sense? So, but what is this? What is this but that's equivalent to P implies not Q? Prove to yourself that that's true, right? And so you have another thing that is part of your, like you have another hypothesis now. Like implication implies another implication. Assume this implies an implication. That's kind of cool. What you can do then is bring out this hypothesis, right? You can bring out this thing, all right? There's a way, okay? So you can bring this, oops, what did I just do? You can bring this hypothesis back out to be by the other one, all right? So, okay. So what is this trying to say, first of all? This guy. If R is false, then P is false or Q is false. That's another way to say this one, all right? But there's more options, and that helps when it helps to have options when you're trying to prove something, right? So that's what that means. But this is also equivalent, all right? You can really bring this back over, right? Like this is like, let's read the English. Like not R implies P implies not Q. So if not R, then if P, then not Q. So it's kind of like ifing two things. It's assuming two things. Does that make sense? So just assume them both at once. Assume not R is true and assume P is true, and then prove that not Q is true. That's a hand-wavy way of saying that. But these two things are exactly the same. Okay? I promise. Which is a little weird to think about, but like do a truth table just to prove it to yourself. But like if you have multiple things, you have this kind of thing going on, to compute the contrapositive, you can like get rid of one of them. Okay? You can flip one of them, like flip just this one with this one and negate them. Does that make sense? That's how it's kind of turning into this. And another way to say this one now is if R is false and P is true, then Q is false. All right, so all I'm trying to say is if you have something like this, an alternative contrapositive, instead of doing just this, is this one. Okay? And that's actually going to help you not negate some things in our previous statement. All right, so that's going to help us here. So kind of like we want to keep this one by itself, and so let's do that. All right, let's do that now because we can turn it this idea. Let's do the contrapositive in the weird way now. So let's negate the conclusion always, right? Negate that. Another way to do that, like the normal way, would be negate the conclusion, which is now x divides y plus z. And that implies the negation of the whole darn hypothesis. That's negation of x divides y and x does not divide z. All right, so it looks a little ugly, this part at least. But we can make it better. Let's see, that looks cleaner now. And so now using our rule, right? Using our rule, we know De Morgan's law, sure. De Morgan's law, we get, all right, x divides y plus z. It's a lot of plugging and chugging right now, but we'll get there. Implies, we got, all right, the negation of this is x does not divide y. And then we have ORed with, because De Morgan's law, ORed with, x does divide z, because he, like, double negation. This is a negated divides, or negating it again, back to normal. All right, so we got this one. And when you have this, you can actually bring this negated thing back as a hypothesis. All right, that's what we just showed on the other slide. So this can turn into, and this is probably the best way, because you don't have any negated divides anymore. This can finally turn into x divides y plus z and x divides y implies x divides z. And that can be our inner thing here that we prove. Okay, that's our... You see how there's no negated things, no slashes anywhere? That's going to be easier for us. All right, so now prove this. For all x, y, and z, this is true. That's our contrapositive. All right, assuming you gave it a try, let me do it. Proof. So assume, we got to make assumptions, assume, introduce these variables, assume this is true, assume x, y, and z exist, and that this is true about them. So assume x, y, and z are integers, so we also have that about them, right? Are ints. Assume this is true and this is true. All right, assume that x divides y plus z. And finally assume that x divides y. That's another assumption, because it's a direct proof now that we've gotten it into a different kind of implication. And x divides y, finally. All right, what do we need to show now? Under all these assumptions, we need to show that the conclusion is true. Assume the hypothesis is true, prove that the conclusion is true. So what we need to show right now to complete our proof is that x divides z. All right, that's the end of it all. So now let's unpack all these definitions, because that's usually what you should do, and then we'll try and make this happen. Right? What does it mean for something to divide something else? So something divides something else when, so x divides y when y is equal to some integer multiple of x. Okay, call it k. That's what we're doing here. So let's unpack these. What does it mean for x to divide y plus z? Well, that means that y plus z, right, is divisible by x. That means y plus z has x as a factor. That means y plus z is equal to x times some integer. Let's put it at the front. Equals k times x. Does that make sense? For some integer k. And then we also know that x divides y. So we also know that. And all right, that means y must be equal to some integer times x. And it's a different integer. It does not have to be the same one. It's got to be a fresh variable name each time. M times x. All right. For some integers, k and m. Don't know what they are, just know that they're integers. For some ints, k and m, let me write ints better. All right, I got those guys. I know that about them now. What do we want? X divides by z. Or x is divisible by z. Sorry. X divides z. That's what I'm trying to say. Too many terms. What we want to show that is that x divides z. Another way of showing that, right, is showing that x showing that z is equal to some integer times x. Let's call that r. See, if we had that, that would show that x divides z. That's what it means for x to divide z, according to our definition. All right, so that's what we're aiming for right now. We're trying to set up an equation that looks like this with what we know. All right, so we know this, we know this. Let's try and make it happen. So what is, okay, we have y plus z. Y plus z is equal to k times x. Okay, it's equal to k times x. Let's see, what could we do with that? But we also know that y is equal to m times x. So let's plug that in, all right? Y plus z, well, y is equal to m times x, so that's equal to m times x plus z. You just got to play around until you find something. So m times x plus z. All right, that's making some sense. What is this equal to? Well, the whole darn thing, right? Y plus z is still equal to k times x. So I'm just setting up all the equations that I know. This whole thing is equal to k times x. You see that? So I've got all these three equations happening at once. And I can get z by itself now. You see that? I can get z by itself by using this equation and subtracting, taking this equation that I just have now, and subtracting mx from both sides. So minus mx from this side to get z by itself. You got to bring it over to here, of course. So what do I have now? I have z is equal to kx minus mx. K times x minus m times x. Okay, so I got that. And I'm looking for something that looks like this. I need x times something, some integer, to make z. Can I factor this? Yeah, I totally can. Factor an x out. So this is equal to k minus m times x. And what is this? I'm just looking for z to be equal to some integer times x. This bad boy right here, that's an integer. Does that make sense? That's how you find it, okay? So z is equal to an integer minus an integer is an integer. It's equal to an integer times x. So that means z is divisible by x. Dun, 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 or x divides z. That's another way of saying that. All right, that's the idea. So z is equal to, therefore, we know that z is equal to k minus m. We just discovered this. K minus m. What do we got? K minus m times x. And this k minus m can serve for that r, serve the purpose of that r. And we know that k minus m is an integer. That's the other part of the divisibility thing. Is an int. So that proves that x divides z, according to the definition of divides. That works out. And that's what we needed to show. We've shown it. So QED, mic drop. We did it. Hooray. So that is a proof by contrapositive, and it would have been so ugly to do it this normal way, right? Because you got some negations in here. It makes no sense even. So that's why the contrapositive is your friend. So there's that. Yeah, hopefully that made a little bit of sense. I want you to try this one. It should be a little bit easier, okay? Prove it by contrapositive. So for every non-zero real number x, if, here's your if then, if x is irrational, then 1 over x is also irrational, okay? So that's the idea. That's what we're trying to prove. So irrational just means it's not rational. A rational number, we know what that means. So that's why we want to like do the contrapositive and like switch it up. So we have, let's see, a rational number is one that's the ratio of two other numbers. So it looks like it's some integer over an integer, okay? That's what it means to be a rational number. So, where were we? Here we are. So for every non-zero real number x, if x is irrational, then 1 over x is also irrational. So try and compute the contrapositive and try and prove it. All right. All right, this is your P, this is your Q, and all right, I'm going to do it quicker. I'm not going to write out the math this time. I think you're getting it, all right? So what's the contrapositive of this? Well, it's assume the negation of the conclusion. Not P implies not, or sorry, not Q implies not P. So it's 1 over x is, if 1 over x is rational, then x is rational. Do you see that? The negation of irrational means rational. So, all right, I'm going to do a direct proof. So I'm going to assume that this negation thing is true, right? I'm assuming not Q. Assume not Q. So what is not Q? Assume that 1 over x is rational. All right. We also know that this x is non-zero, so we need that as well. So assume x is non-zero, so it's not equal to 0, and that 1 over x is, because that's not Q, right? I'm assuming not Q. I'm doing a proof by contrapositive, a direct proof by contrapositive. So I computed the contrapositive. Now I'm doing the direct proof from it, assuming the hypothesis, assuming not Q. 1 over x is rational. And what we need to show, we need to show that not P is true, right? Because that's the conclusion of your contrapositive. Show that x is rational. X is rational. That's what we need to show to complete the proof. So, all right, what do we know? What do we know? So we're assuming that 1 over x is rational. Cool. All right. So first of all, what we did was we computed the contrapositive. That was, all right, 1 over x is, it's the negation of Q. 1 over x is rational. Implies x is rational. That's the contrapositive. That's the contrapositive. So this is, we're assuming this right now, and we're trying to prove this. That's what we just said. All right, so when you're rational, that means you're the ratio of two numbers. You're equal to something over something else. Go back to our definition. That's equal to two numbers, where that second number was not 0. That can't divide by 0. So what do we got? So 1 over x must be equal to m over n, let's say, for two integers m and n. For some m and n, which are integers, and then also n can't be 0, right? N is not equal to 0 because you can't divide by 0. And if that's true, that won't work out. All right. Okay. So I need to calculate that x is rational. All right. So, but I don't know. Don't really need to say but. I just need some conjunction here. But what is x? X is 1 over. That's the inverse of this. X is equal to 1 over 1 over x. Does that make sense? That's totally fine. X is equal to 1 over 1 over x. Sure. Which is equal to, I know that 1 over x is equal to m over n. Is equal to 1 over m over n, which is, that's just the flip of it, right? Which is equal to n over m. Does that make sense? That's what x is. X is equal to n over m. Okay. And I also need to show like this works out, because I'm trying to show that x is rational, right? That it's equal to a ratio of numbers where the number on the bottom is not 0. So I need to show that this is not 0. M cannot be 0. Okay. So that works because m over n is not 0, right? Because 1 over x is not, no, sorry, excuse me. Let's see, 1 over x is non-zero because x is non-zero. Does that make sense? 1 over x must not be 0. 1 over x is non-zero. So its reciprocal is also non-zero, all right? So that means m over n is not 0. Same for m over n. So I can divide, I can take the reciprocal of this. I can divide by this. It's totally fine because it's not 0. Okay? So I've just found that x is a ratio of two numbers. There they are. They're derived from 1 over x, of course, naturally. But I've shown that they work out and that m is not, or m cannot be 0 because of these facts. Okay? Don't know why my screen's flickering like that. But we know that this works. You can divide by this. This is totally fine because it's non-zero, which means that neither of these can be 0. Okay? So x is rational. Isn't that fun? That's so cool. QED. So that's a nice proof of the contrapositive, I think. Okay? So with that, I want to show you probably the coolest proof technique in this class. It's called proof by contradiction. We needed to do direct proof first, because it's kind of like direct proof in a weird way. But proof by contradiction, oh man, does it works so weird, it just makes things feel like magic. This is so cool. I'm excited to teach it to you. So, alright, surprisingly, proving something false can help you prove true things. Something that's false can help you prove truth. It's a weird philosophical idea, I guess. Here's proof by contradiction. It's a valid strategy, and I'm going to try to show to you on this slide why it's valid. Right? In a proof by contradiction, you assume that your entire theorem, the whole thing that you're trying to prove, right? Assume that that whole idea is false. Assume that it doesn't work out. Assume that you're in a universe where what you're trying to prove is false, and then find a contradiction. And the second you do, that means the theorem must have been true. It's really weird. Let me try to prove to you how it's valid. All right. So if your theorem statement is Q, what you're trying to do is you're trying to prove this, right? That's assuming this. That's trying to do a direct proof with this kind of implication, right? Assume not Q, prove false is true. See that? You're trying to prove that false is equal to true, which is of course nonsensical, because we know false is not true, and that's your contradiction. Okay? Try to prove that false is a true statement, which doesn't make sense. All right? Well, let me try to show to you why this works. All right, one way to show that this is a valid statement, that this is equivalent to your original theorem statement Q, right? Because that's what you're really trying to prove. What is this? Right? This is equivalent to, do the contrapositive. It's negate this. True implies Q. Assume true. That's assume nothing. Implies Q. That's equivalent to just Q. Another way to do that is saying, all right, what's this? This is not the hypothesis, so not Q or false. And ORing with false does nothing, so that's just not Q. Double negation gives you Q. So this is equivalent. This idea is equivalent to just proving your theorem. It's not intuitive at all, especially when we use this as a proof. But our goal is to prove that false is true somehow. Okay, and that's how you do it. That's your contradiction. And so false, proving that false is true, looks something like this. You're proving that two things that can't be true at once are both happening. Right? You prove that two contradictory things that can't both be true, you prove that they both are true under this weird assumption. Right? That gives you, like, this is equivalent to falsehood. Right? Hopefully you remember that rule. That kind of thing. Then you're done because you've just proven that false is true, and this whole idea of this proof theorem was equivalent. This whole idea of this proof technique was equivalent to your original proof. And then you're done. And it feels like there should be more to it. Okay? But that's why it's called an indirect proof. It feels weird, but it works. All right? Also, true implies Q. That's equal to Q. Let me prove that to you. If that's not obvious. True implies Q. That's equal to not true or Q, which is equal to false or Q, which is just Q. Right? Because false ORed with anything is useless. Just Q. So that is also another way to go about proving that this proof technique, assume the negation of the whole theorem, derive false being true. That's your contradiction. That's what it means. All right. So let me show that to you. It's going to be really cool. All right. I have probably one of the most fun proofs in this set of slides in this lecture. So cool. Here's our first example. Let's talk about birthdays. All right. We're going to use a proof by contradiction. All right. So here's my theorem. Among any group of 25 people, there must be at least 3. Right? There must be at least 3 who are all born in the same month. All right? And we're going to prove that this is true by contradiction. All right? So again, we're going to assume that the whole theorem is false, and then we're going to find a contradiction. So what's the first of all, what's the theorem? All right? There must be at least 3 people who are all born in the same month. What's the negation of this? Right? Let's say this. Among any group of 25 people, there must be at least 3 people who are born in the same month. So it's trying to say, like, there is a month. There's a month, call it M, where it's got greater than or equal to 3 people born in it. In your group of 25. All right, that's kind of the statement. And so we're going to assume the negation of all of this. Assume that this is not true. What does that mean? All right. Assume that every month M, because this turns into a for all, assume that for every month M, there must be the negation of this. This must not be true. There must be less than 3 people born in M. That's what we're going to assume. That's the negation of the theorem. You see that? So, proof. Usually you want to specify that we're doing this by contradiction so that, like, your reader of your proof can, like, mentally prepare for how weird this is going to be. All right, proof by contradiction. Let's go. So, all right, we're going to assume that that this is false. Assume that our theorem is false. So assume this whole thing, the negation. Assume that this idea is true. Assume that every month in our group of 25 people, for every month, less than 3 people were born in it. All right. So let G, I guess, be our group. G be a group of 25 people. Just setting the scene, right? It's supposed to work for any group. So let G be that group. 25 people. Let me write people better. And, well, assume that less than 3 people were born every month. Assume. Less than 3 people were born. Less than 3 people in G were born in each month of the whole year. What does that mean? See if you can derive the contradiction before I tell it to you. In each month. You see how there's a contradiction there? Then, all right, what does that mean? Then, the maximum number of people in G, right, is, well, if there's at most 2 people per month, what does that mean about the size of G? Then, the max number, if we're assuming this, we're in this universe where this is true, then the max number of people in G is, well, what's strictly less than 3? It's the first number strictly less than 3 is 2. There's 12 months, is 12 times 2, which is equal to 24. We've just proven that the maximum number of people, we've just shown that 24, right? That's the size, the maximum number of people in G is 24. So we've shown that, well, let's see. Whatever 25 is the size of the group, that better be less than or equal to 24. That's essentially what we just proved. You see that? And that's a contradiction. That's a contradiction. So some people legitimately in their proof, they say contradiction, exclamation point. Alternatively, so see how this is not true. We've just derived that false is true. Alternatively, there's a cool symbol in typesetting. It's a lightning bolt symbol. So some people like write a little lightning bolt with an arrow at the end to mean contradiction. And the second you've derived false, you've proven the theorem. You're done. Proved. QED. You've just shown that, all right, this assumption that it's not true was incorrect. It must have been true. It must be that in any group of 25 people, there must be at least 3 who are all born in the same month. And you went about proving that in a really weird, roundabout, backwards way. Does that make sense? So that is really odd, and that gives us what we wanted, though. Isn't that amazing? So that's our first proof by contradiction. It feels wrong. I promise it's going to make more sense the more you do it. But with that, I have I'm leading us to a very cool idea. All right. A very cool proof, but let me show you one cool thing first. If you have a big implication with a bunch of like things in your hypothesis, assume all these things, if this, then this, if all these things, if A, B, and C are all true, then D is true. If you're trying to negate that, that is equivalent to assume that all the hypotheses are true. It's all the hypotheses are true and not D. This big thing. The negation of this implication is take all the hypotheses, keep them, and end it with the negated conclusion. All right, this is going to help us eventually. So how? Let me walk you through it. So we got all this, right? That's the negation of all this. We're going to push the negation inwards, aren't we? So first of all, the implication itself is not the hypothesis ORed with the conclusion. Then we're going to push this negation inwards because we have De Morgan's to talk about. So you go to this one and this one. and you flip the or to an and, so it's not this, anded with the negation of the conclusion, and of course the double negation goes away. You see how that turns into your original hypothesis anded with the negation of the conclusion, all right? And this A and B and C could be anything. It's just like could be like 5 things anded together, a million things anded together. It could be 2 things. It's fine, all right? And so essentially what I'm trying to tell you is that the negation of an implication that looks like this, more or less, is equivalent to P and not Q, okay? Because you're going to be negating your entire theorem, right, for a proof by contradiction, and usually our theorems look like implications, and so you're going to have to negate implications that look like this. And so here's how you do it. Like P was potentially some large thing. That's fine. You just keep it along for the right. All right, that's the goal. Yeah. So with that, I would like to prove to you the coolest proof. Probably one of the coolest proofs in this class. All right. So it's a classic example that everybody learns. It's a proof by contradiction. It's really weird, but it's so cool. All right, we're going to prove that the square root of 2 is an irrational number. It cannot be written as the ratio of 2 numbers. All right, so an irrational number. This means it can't be a ratio of 2 integers. The square root of 2 is irrational. All right. To prove this, we're going to prove it by contradiction. All right, and we're going to need a little helper proof called a lemma on the next slide. I'll talk to you about that in just a second. But all right, let's start off this theorem at least. All right, proof. We're going to do it by contradiction. Proof by contradiction. And so what does that mean? Here's our theorem. Square root of 2 is irrational. Assume, in our proof by contradiction, assume that our theorem is false, and then we're going to derive a contradiction. Prove that false is true. So what's the opposite of this? Square root of 2 is irrational. Well, that square root of 2 is rational. So by contradiction, assume that this is not true. Assume the whole theorem is false. Assume square root of 2 is rational. We're going to derive a contradiction from this. All right? We'll get there. But we need a little helper idea on the next slide, and we're going to prove a little smaller theorem called a lemma. All right, so here's our lemma that we're going to prove. The word lemma, by the way, it's a word that's in math books. It's just like a little theorem. You use it to prove the big thing that you're trying to prove. So we're going to use this lemma. It's just like a little theorem that's going to help us prove this big thing. Okay, so here's our lemma. If x squared is even, then x is also even. All right, so here's the proof. It's going to be by contrapositive. It's easier. Proof, and we're going to do it by contrapositive. If I can spell contrapositive correctly within these guys. All right. So, all right, how do we do this? We have, all right, contrapositive of this is assume negation of this, prove negation of this. Yeah? So it's x is odd, x is not even. So assume x is odd. And we're trying to show that x squared is odd, right? Negation of the conclusion, or negation of the hypothesis becomes what we're trying to conclude now in the proof by contrapositive. So assume x is odd, we're trying to show that x squared is odd as well. And apparently this way is easier. So, all right, what do we know if x is odd? Then x is equal to, well, 2 times k plus 1 for some k, that's an integer. And now let's square it, right? So x squared is, well, that's that squared then. X squared is equal to 2k plus 1 squared, which is going to get disgusting, but we'll power through it. That's equal to 4k squared, right, plus 4k plus 1, all right, which is disgusting. And I can factor out a 2 from here, right, because I'm trying to get oddness, right? So I can factor out a 2 from these first two things involving k. So 2 times 2k squared plus 2k plus that 1 still. And I've just discovered that x squared is equal to 2 times an integer, right? This is totally an integer if k is an integer. You can square, you can add stuff, multiply by other integers, it's still an integer. Plus 1, that's all you need to do to show that x squared was odd. See that? So x squared is odd. So x squared is odd. QED. Mic drop. So that's our lemma. If x squared is even, then x is even. We did it by contrapositive. We did like, if x is odd, then x squared is odd. But we've just proven this. All right, so that's fun. Cool. Now let's go back to this proof. We're going to use that. You're going to use that fact in just a second. All right. So this is going to look really weird. It's just a really fun proof. So, all right. Assume that the square root of 2 is rational. We're going to derive a contradiction. All right. What do we know? If we're assuming that it's rational, so what do we know? If square root of 2 is rational. So, all right, that means if it was rational, if we're assuming that it is, square root of 2 is equal to a over b for two integers, a and b, right? Where a and b, or like b is not 0, all that fun stuff. For some a and b that are integers. And we can also impose some side conditions, because like this is just a fraction, right? Let's just assume that we've reduced the fraction, right? That's totally fine to do. Such that a over b, whatever it was, is fully reduced. This is going to be very important in just a second, asking for this. It doesn't matter. Like if somebody told you this is going to be the crux of the theorem, it's so cool. This idea is going to make it all fall apart. It's just really fun to think about. All right, so assume that it's fully reduced, which means like, all right, if a is 10 and b is 20, like reset them, because that's not fully reduced. That's 5 over 10. That's not reduced. It's really all 1/2. That's your fully reduced fraction that looked like that, right? That's what it means. Like, pretend that a and b were fully reduced. You can always fully reduce a fraction. All right. So that's the idea. So all right, if square root of 2 is a rational number, it looks like this. And let's just reduce it and say that a and b are the fully reduced form. All right. That's the idea. So we have this equation now. Let's square both sides so that we don't have to deal with square roots. So so just 2 now is equal to a squared over b squared, because we squared both sides. What does that mean? So we can solve for stuff. So like, we got 2b squared is equal to a squared. Yeah? 2b squared is equal to a squared. What does this tell you? This is kind of weird. A squared is equal to 2 times some other number, which means a squared is even, which is weird. All right, so a squared is even. Cool. All right. By our lemma, if we know the squared is even, then the thing itself was even. By our lemma, that means a is even. See that? By the lemma, a is even. I swear I'm going somewhere with this. Think about fully reducing things. By the lemma, a must be even. All right, we've shown that. So what does that mean about a? So a is equal to 2 times some integer. Call it k for some integer k. All right. And then here's something I know about a and b at the same time. 2b squared is equal to a squared. All right, so 2b squared is equal to a squared, which is just 2k now. We know that. Which is equal to 2k squared, which is equal to 4, right? 4k squared. And so I have that, right? 2b squared is equal to 4k squared. Cool. If I divide this equation, this equal to this, by 2, what do I have? That gives me that b squared is equal to 2k squared. All right, you see that? What do you know? B squared is equal to 2 times a number. So b squared is even. See that? So b squared is even. See, I'm just learning new things, and this is all going to help everything fall apart. So b squared is even. By our lemma, that means b itself was even, right? Because if you have something squared is even, then we've proven that that thing itself without the squared is also even. So b squared is even. B is then even by the lemma. So b is equal to 2 times something. Call it m, all right, for some integer m. Do you see what I just did? I've shown that, all right, if square root of 2 is a over b, I've shown that a is even and b is even. A looks like this, b looks like this. Do you see the problem? Because I've assumed it was fully reduced. So, therefore, square root of 2, well, we said that was equal to a over b. But what's a but 2k? And what's b but 2m? So that's equal to 2k over 2m. And now this is a problem. I assumed that a over b was fully reduced. Do you see how it was not now? This can still be reduced. I can factor out a 2 from this. So somebody lied to me. Math lied to me by saying, well, I assumed that was fully reduced. That's not true. It wasn't. This can still be fully reduced. Or, this can still be reduced. It's not yet fully reduced. So that means a over b was not fully reduced. Though I thought it was, though it was claimed to be, I assumed that it wasn't fully reduced. So I have that at the same time, a over b is fully reduced and a over b isn't fully reduced. That's false. Can't have both. So I've created a contradiction for myself. I've proven that false is true, QED. Therefore, this assumption was incorrect. It must have been the case that my assumption was false and the theorem was true. All right? So square root of 2, therefore, is irrational. Isn't that so weird? It just feels wrong, like we're done now. But that was all we needed to do. We just needed to derive a contradiction after assuming the theorem was false. And that gives us the proof. So weird. So cool. All right? That's a very exciting, mind-blowing theorem, I think. It's a classic one. Hopefully you had some fun there. Obviously, I wouldn't ask you to come up with a proof on the fly like this on a test, but that's just a really cool example of a proof by contradiction. Like, you can't prove it any other way. Okay, so yay, there's that one. Let me have an example for you now to try. Do this by contradiction. It's going to be very similar to the birthdays example. So, all right, here's the statement. Prove it by contradiction, please. If a group of 9 kids have won a total of 100 trophies, so, I don't know, their parents really like them to play sports or something. If a group of 9 kids, among themselves, they've won 100 trophies, then at least one of the 9 kids has won at least 12 trophies. All right? So that's the idea. This is going to be a bit hard because you want to assume that this whole thing is, let's see. You want to assume that this whole thing is false, right? So it's like an if-then. The negation of the direct proof is just assume this and also that the negation of the conclusion was true. That's how you get the falsehood, all right? That's how you negate it, so remember that. So it's like all this implies all this wavy stuff. So the negation of this, because you're going to assume the negation of this, is just like take this, and the negation of this, all right? So you're going to assume this and the negation of this, all right? That's pretty much the idea. So assume this part, just keep it as true, and then like this could be the thing you do proof by contradiction on. You're going to have the negation of it, all right? Proof by contradiction. That's another way to think about it. Because it's like you're in a direct proof now, and you're like, you've got P, you assume P, and now you have Q to prove. You can prove the Q part by contradiction just by assuming that it's not true. That's another way to think about this. But at the end of the day, you're really just negating an implication, if you want to think about it that way. So either way works, but just like assume this first part and prove the rest by contradiction. So assume that this is not true, this last part. All right? So give that a try. See if you can find the falsehood, find that contradiction. So, all right, here's our proof. So again, you probably want to specify by contradiction. But all right, assume that you've got a group of 9 kids that have won a total of 100 trophies, and also assume that this is not true. At least one of the 9 kids has won at least 12 trophies. What's the negation of that? That means that every child has won, let's see, at least 12 is greater than or equal to 12. So the negation of that would be, what's the negation of that? That gives you, that gives us less than 12, right? So assume that every child has won less than 12 trophies. Assume all 9 kids. Some more informal proof, but everything's there. So assume all 9 kids won less than 12 trophies. You see how that's the negation of that, the opposite? We're going to derive a contradiction from that because it's like there's not going to be enough now. 9 kids. I'm sorry, my handwriting. Not doing the best right now. 9 kids won strictly less than 12 trophies among all of them. Each of them won strictly less than 12. See that? That's the negation of at least. It's like, that's a there like this, now it becomes a for all. Assume all 9 kids won less than 12 trophies. Okay? So that means at most 11 trophies per child. Do you see the contradiction now, if you didn't see it before? So then, the total number of trophies was at most 11 times the 9 kids, so 11 times 9, which is equal to 99. But we said, we're assuming, right, that there were 100 trophies total. But there were 100 trophies total. Do you see how that's a contradiction? We're assuming that there are 100 trophies total, but we've also shown that there can be a maximum of 99 of them. That is a contradiction. Those two statements are contradicting each other. We've just proven that false is true, nothing is as it seems, and so that means the theorem that we were trying to prove is true, that this assumption that this was false was not correct. So that means the theorem was true. Then at least one of the 9 kids won at least 12, because you got to like bring over that extra one that would give the 100 to somebody, right? The 100th trophy would belong to somebody. Okay, that's how it would work. So that's the proof, and hopefully it's making a little bit of sense. See how it's very similar to this birthdays example? There's an underlying idea here called the pigeonhole principle that we'll get to later in the class as well. But that's enough for now. So yeah, with that, let's talk about a few more things, and then that'll be it for these slides. So let's talk about proof by cases. Sometimes when you're doing a for all, right, you're doing a for all proof for all x, p of x is true, it's hard to prove this because like the first step is like assume x is an arbitrary element, prove that p works for x. Sometimes it's hard to do that for just one x, for one arbitrary element. Sometimes your domain, like here's your domain, sometimes it splits nicely into like a few different groups, like a bunch of things that look like this thing, a bunch of things that look over here, look similar to this stuff, and a bunch of things over here, right? Maybe your domain splits into like a few different concepts. What you can do to still prove a for all is like assume like pick an arbitrary element here, pick an arbitrary element here, pick an arbitrary element here, like have it check out for each of those little sub pieces of the domain. You can still do that, all right? That's what you can do. You split the domain into different classes, we say, and give a different proof for each class. Maybe these are still infinite pieces, but you can give a different for all proof for each of them because maybe the proof goes differently depending, okay? So here's a great example of that. Assume that like your predicate, you're trying to prove stuff about the integers. Sometimes it's easier to give a different proof for the 3 different kinds of integers, right? Like sometimes it's easier to prove stuff about negative numbers, like something works out there, and that's different from proving about positive numbers. And then like 0 is a special case. Like you can have a different proof for each of these different kinds of numbers, and as long as you give a proof for each of them, together they make up all of the integers. Do you see that? So together, they cover it. Together, cover all the ints. And you can have a different for all proof for each of them. And you just bring them together at the end. That's the idea. All right? As long as your proof covers every x value, it's totally fine. All right? So as an example, let's define something. Let's make a definition by cases. That's totally possible. It doesn't have to be just a proof. Let's define that the absolute value of a number, let's talk about what that means. Define the absolute value of x to be 2 things. You got 2 cases, right? Define the absolute value of x to be just x itself if it's already greater than or equal to 0, if it's a positive non-negative number, and define the absolute value of x to be negative x if x is less than 0, all right? Let's prove that for every number, every integer, even real numbers, the absolute value of that number is greater than or equal to 0. Right, let's make that proof. And we can do it by cases. I'll do it down here. Don't need much space. Proof. So we got two cases, right? Because there's two ways to do an absolute value. Either, like it's just according to the definition, like this happens if it's greater than or equal to 0, this happens if it's less than 0. Okay? So proof, you got case 1. Let's prove that this is true, that the absolute value of x is 0 is greater than or equal to 0 if x is greater than or equal to 0. That's your case 1. And then your case 2, we'll do the same proof. We'll prove this about it. The absolute value is greater than or equal to 0 if x is less than 0. That's the other way to do an absolute value. Case 2, x is less than 0. Do you see how these two cases together cover all the integers, all the real numbers even? And if I just do both cases, I've done the proof, right? So, all right, if this is true about x, then the absolute value of x, I'm trying to prove this. I'm trying to show this in both cases, right? Absolute value of x is greater than or equal to 0. It's not negative. So absolute value of x, in this case, if x is greater than or equal to 0, it's just defined to be x. Absolute value of x is x itself, which we already know, right, is greater than or equal to 0. And so we've shown that absolute value itself is greater than or equal to 0. So that case checks out. Boop. And then this one, in the flip case, the absolute value of x, if x is less than 0, is negative x. That's equal to negative x. And that is, well, we know this is true. We can massage this to show something cool. So if we know that x is less than 0, if we negate that, we know that negative x is greater than 0. Do you see that? Negating both sides does that. It gives me this idea. It gives me that fact. So I know that negative x now is greater than 0. Which is totally, I need to show that it's greater than or equal to 0, that the absolute value is greater than or equal to 0. I know that it's strictly greater than 0, in fact. That's stronger. So it's totally also greater than or equal to 0. All right. So now I have that absolute value of x in this case is greater than or equal to 0, which was what I needed to show. And so that case checks out. And I've proven both my cases. And so I've proven the thing. You see that? It's split up into two very easily for us. And sometimes that's still fine, right? Because there's still two infinite ideas, but we've covered both sides of it, right? And that works out. All right, so that's proof by cases. That'll be useful. Another interesting proof technique is called W-log for short. It stands for without loss of generality, okay? Because sometimes you got a proof, and it's like you gotta, like it splits up into cases maybe. You got a proof that splits up into cases. Maybe you got multiple cases, at least 2. Could be 3, 5, whatever. But you got a proof with cases, and like you show, like this case, the proof looks like this. I don't know, I'll draw a picture of a person. Like, this is the proof for this case. And over here, it looks like this. And it's really the same case, just slightly different without any real reason for being different, all right? And the proof just like swaps some things out. The proof looks exactly the same because the two cases look really similar, all right? It's just obvious that both are true. If you just prove this one, it's obvious that this case is also true. So W-log gives you that idea. You will log the answer. You say, without loss of generality, just assume we're in this case because this case is obviously also true, okay? So here's an example of using that, and we'll see, like, it's obviously, like, if you prove one side, the other side works too, okay? So for any two integers x and y, if x is even or y is even, then xy is even, all right? So the idea is, for any two integers x and y, if x is even or y is even, then x times y is even. So it's like, this is really two separate proofs. It's like, all right, if x is even, then show that xy is even. And then if y is even, show that xy is even. See that? That's kind of dumb because these are variables, right? If you just did this one, just swap x and y and this proof would go through. Does that make sense? That's the idea. So that's why you don't really need this second case. Just do one, all right? So assume, what you do when you notice that idea is just assume without loss of generality that x was the one that was even, right? Because it's just like, it's an implication. It's either this one or those are your two cases. Assume without loss of generality that, we'll log, that x was the one that was even. Does that make sense? And then what we need to show now, we need to show that xy is even. X times y is even. Boop. So all right, assume that x is even. So then x is equal to 2 times k for some integer k. You know the drill, right? X times y, that's equal to 2 times k times. You just multiply this by y, right? Equals 2 times k times y. And I'm looking for that this is even, right? And xy is equal to 2 times something. 2 times an int. There it is. There's another integer. Plug that in, and now we know that xy is even. You see that? It's 2 times some integer. So therefore, xy is even. And do you see how it would just have been wasted thought to do the other one? Just like, all right, the other case is assume y is even, show that xy is even. There's no difference in the proof, right? Do you see that? Because if you just swap x and y, the proof is just so you copy and paste it, right? Swapping x and y in the proof would give you the same idea, right? Proves the other case. Swapping x and y in the proof to the left, on the left, proves the other case. So there was no need to do that second case, right? It's obviously also true. So we say that without loss of generality, assume that x was the one that was even. And then we have to write half as much. It's perfect. So just prove one case without loss of generality, it works out. QED. Okay? So make sure it's simple, right? It really is just changing variables around. That's when you get to use without loss of generality. You don't get to use without loss of generality when you just can't figure out the other case, okay? Don't try to trick me. It's got to be the same. It's got to be very symmetric, okay? So that's that one. And then here's my last example for you to try. So prove this statement by cases, please. So if you got x and y, integers x and y, assume that they have the same parity, then x plus y is even. So the same parity means that either they're both odd or they're both even. Like if you look at their last bit, it's either a 1 or a 0. They're both either both odd or both even. Okay? So if x and y have the same parity, those are your two cases. You see that? Kind of. Then x plus y is even. So I've given you enough hints. Give that a try. So here's the proof. All right, we got two cases, right? Either x and y are both odd or they're both even. So case 1. And you're assuming they have the same parity. So assume that they have the same parity, so they're either both odd or both even. Those are your two cases. And then we're proving in each case that their sum is still even, right? Case 1. Case 1, where they're both odd. And case 2, where they're both even. We've got to prove both cases. It is not without loss of generality. It's different. Both two different ideas. Because unraveling the definition of odd and unraveling the definition of even is going to do different things, right? So case 1, they're both odd. Assume x and y are odd. I'll go through this quickly. What does it mean? Just unravel all the definitions. That will eventually lead you to the answer. So x must be equal to 2k plus 1. Let me write that smaller. 2k plus 1. And then y is also equal to 2 times something plus 1. Not the same k, though. It's 2 like m plus 1, let's say. And then we need to show that the sum is even if they're both odd. So x plus y is equal to 2k plus 1 plus 2m plus another 1. Simplify that to be 2k plus 2m plus 2. You can factor out a 2 there. That's equal to 2 times k plus m plus 1, which is 2 times an integer. And that means that x plus y was even. It's 2 times an integer. See that? So x plus y is even. And that is that case proven. Let's do the other one. So if they're both even, so assume instead, in this case, that x and y, they have the same parity, but they're both even. Assume x and y are even. This will still work out. So in that case, x is equal to 2k and y is equal to 2m. For some integers k and m, you add them up, x plus y, that's equal to, just plug them in, 2k plus 2m. And you can, of course, factor out a 2 from that as well. 2k plus m. So x plus y is equal to 2 times an integer. Therefore, x plus y is even. So x plus y is also even in this case. Boop. And that checks out that case. I've proven both cases, both ideas that I needed to show for having the same parity. And I've shown that x plus y is even in each case. Therefore, the whole thing is true. The entire statement is true. And we proved it by cases. Okay? Please yell at me if you have any questions about that stuff, but hopefully, especially with my examples, you're kind of getting a feel for how proofs work, like what you got to think about, the strategies involved. Usually, honestly, the answer is almost always unravel the definitions first, because then you have some equations to work with. All right? But you know a lot. You have a lot in your tool belt. Direct proof, very important. Can't forget it. Proof by contradiction, also a huge one. Very helpful as well. Those are the two big ones. And now you know them both. So that's all that I want to say about proofs. And that's as much as I want to melt your mind in one lecture. So I'll see you next time.